Yes.
English.
Yes. I remember. Okay, so it's a pleasure to have with us today Clement Erignoux from Lille. He's going to talk about something about active matter.
Okay, so first let me thank the organizers for inviting me to give this talk. It's a pleasure to be back, at least remotely, in Brazil. So I must apologize because what I'm going to talk about in parts, I already talked about, including in Rio at some point, but it was right after my PhD. There has been a few developments since then, so I thought I'd revisit the topic. So I apologize for those who have already seen at least parts of my talk. Hopefully, I'll put things in a bit of a new light, and maybe there will still be some interesting information. So I'm going to talk about, oh yeah, by the way, if there are any questions, please don't hesitate to interrupt me. So I'm going to talk about active matter. This is going to be my general topic. And in particular, I'm going to talk about phase separation in active matter. So first, I'm going to define what I mean by active matter, which is a terminology coined by physicists. And then I'm going to present successively a couple of models which are somewhat active matter-ish and which behave the way active matter does. And I'm going to talk about a little bit how hydrodynamic limit theory allows you to derive some interesting information about phase separation and the phase diagram for these models. Okay, so let me first introduce briefly the notion of active matter. So active matter is a terminology, as I mentioned, that was coined by physicists. And the initial motivation behind active matter was the study of collective behavior. So at that time, the models were not called active matter, but it was essentially the first models for active matter. Okay, so think about schools of fish and flock of birds and stuff like that. And actually, active matter can represent what happens, of course, in collective dynamics, but it can also represent a lot of physical and biological phenomena. So it's a very large class of models in substance. So a very rough definition of what active matter is. So you can imagine a number of individuals, a large number of individuals, and each individual is self-propelled. It's gonna travel in a specific direction. And the specific direction is going to evolve in time, and each individual is going to be able to consume energy in order to maintain this self-propulsion. And each individual is also allowed to interact with its surroundings. So the direction, in particular, of the self-propulsion is going to be able to evolve depending on what the individual sees. Okay, and the reason why active matter has been the subject of intense scrutiny in recent years or decades is that because it has a pretty rich phenomenology. And so there are two main phenomena for active matter. The first one is alignment phase transition, which is roughly the idea of a school of fish. So you have fish that interact locally. And in the end, what you observe is a general collective behavior for the school. But that's not the phenomena I'm going to be interested in today. And the phenomena I'm going to be interested in is going to be motility induced phase separation. Okay, so this is a coarsening phenomenon, which I'm going to talk about a little bit more now. So the idea behind motility induced phase separation is that imagine that you have, so your active agents, your active individuals, and imagine that their velocity, the speed at which they move, depends on the local density. So if it's quite a natural thing to expect. For example, if you think about biological individuals, they're going to tend to slow down in regions which are more crowded. And the idea behind MIPS is that if this happens, if you have introduced a slowing down mechanism, you're going to have a negative feedback, a positive feedback between slowing down and coarsening. Okay, so the more particles get into crowded region, the more they slow down, and the more they slow down, the more the regions become crowded. And so this phenomenon generates some non-equilibrium and in particular non-diffusive behavior for active particles, provided that there is this dependency of the velocity of the agents in the local density of particles. And this is what I represented schematically here, which is a representation of what are called active Brownian particles. And you see that you have initially some equilibrium lag distribution, And as time goes on, you're going to see this coagulation phenomenon, and particles are going to start packing up. So the motivation behind all the models I'm going to talk about today is to understand this type of phenomenology and to try to understand them from a mathematics point of view, because they are, so this phenomenon of motility induced phase separation, or MIPS. So MIPS has been very well studied from a physics perspective, but mathematically so far, there have not been that many models that have actually been shown to exhibit MIPS. So the problem I'm going to be interested in is, can we obtain an exact phase diagram for a stochastic particle system with purely local interaction? Okay, and I'm going to get back to why it's important to consider local interaction rather than, for example, mean field type interactions. So the first simplification is that we're going to consider lattice gases, because lattice gases have this very nice treatment possible through the lens of hydrodynamic limits, and there is a large toolbox in order to understand their macroscopic behavior. So I'm going to consider lattice gases, where particles are going to hop randomly on a square lattice. And the velocity is going to be interpreted, so I have essentially random walkers, and the velocity of the active agents is going to be interpreted as a drift in the direction of the jumps. And the second simplification, at least in the first part of my talk, is going to be that I'm going to consider only two types of particles. Okay, so now my active agents are just going to be particles which perform random walks on a lattice. And I'm going to consider two types of particles, plus and minus. And the plus are going to travel more to the right, and the minus are going to travel more to the left. Okay, so now let me introduce a little bit more specifically the model I'm going to be interested in. So I'm going to consider a two-dimensional lattice, but for this first example, the dimension 2 is not really crucial. It could be dimension 1, it could be a higher dimension. It does not really matter for this specific model. Okay, so you have a discrete lattice in 2 dimensions, and you see that the spacing here between two neighboring sites is about 1/n. Okay, so I define E1 and E2, which are the basis vector for this lattice. And now at each site of my lattice, I'm going to either have a plus particle. I'm going to either have a plus particle, a minus particle, or an empty site. Okay, so my configuration is going to be given by a family of variable eta x, and eta x is -1 if x is occupied by a minus particle. Eta x is going to be 0 if site x is empty, and eta x is going to be 1 if eta x is if x is occupied by a plus particle. Okay, and later on, it's going to be convenient to define two more variables, which are going to be eta x plus and eta x minus, which are just going to be the indicator functions that there is a plus or minus particle at the site. Okay, so essentially eta x plus is the subconfiguration of plus particles, and eta x minus is the subconfiguration of minus particles. Okay, and now what I'm interested in is the macroscopic behavior of this model. So as the lattice mesh size is over 1/n, I want to send n to infinity and see my lattice as a discretization, finer and finer discretization of the square 0, 1 square. And I want to understand the macroscopic behavior of this model. So hopefully the basic definition of the model is clear. Okay. So for now, I've just defined configurations for my model. Now I need to define first from where I am starting my process. And since I'm interested in the macroscopic limits, I'm going to consider two smooth profiles, ρ0 plus and ρ0 minus, which are going to be the initial macroscopic densities of plus and minus particles. Okay, so of course I drew the figure in dimension 1, but you can imagine that it exists in dimension 2. And so I'm going to call rho, which is going to be the sum of the two, to be the total particle density at a given site. Okay, now you imagine that this is also a smooth function, and you imagine that, okay, you assume that ρ0 plus ρ0 minus is less than 1, okay, because you cannot have more than one particle per site. And now you want to define an initial configuration that's going to fit this initial profile, and a very nice and easy way to do that is just to pick a site x and put a plus particle at site x with probability ρ0 plus over x, and put a minus particle with probability rho 0 minus of x. Okay, so this is what I represented in this drawing here. Okay, so for this model, this is called a state of local equilibrium because you're gonna sample the initial state independently for each site. Okay, so initially, if you look at a local box in your system, it's gonna be a local product state with a given density. Okay, so this is my initial profile, and now I'm gonna get to the dynamics. Okay, so you start from this state of local equilibrium, and now I'm gonna define the dynamics. And hopefully this dynamics is going to model in some way motility induced phase separation. So I need the first part I'm going to need for my dynamics is some steering. Okay, so by what I mean by steering is that any edge of the graph is going to flip its endpoints at rate r. Okay, and since you're interested in the macroscopic behavior, you need to scale up this dynamic in the sense you need to accelerate it by a factor n squared. Okay, so my flipping dynamics is going to intervene at each edge at a rate dn squared. Okay, so the n squared is pretty natural because under these dynamics, essentially, if you consider a single particle, this single particle is going to perform a symmetric random walk. And if you want to leave to your system time to actually have a macroscopic evolution of the profile, you need to, your individual particles need to wait for a time order n squared in order to be able to move over macroscopic distances. And the first remark is that, so this part of the dynamics is going to have an associated Markov generator. And this Markov generator acting on both eta x and absolute value of eta x is going to be a discrete Laplacian. Okay, what I'm saying here is that the model, when you consider it well, the model is gradient, which is very important, as we'll mention later on. Okay, so here recall that eta x takes values between -1, 0, and 1, and absolute value of eta x is just going to be 0 or 1. Absolute value of eta x is just, is there a particle outside x? Okay, so essentially, this is a SEP, the absolute value of eta x. Okay, so this is the first part of my dynamics. This is a steering dynamics. The second part is going to represent the active nature of my lattice gas. And the second part is going to be a weak drift. Okay, so on top of the symmetric jumps, you're gonna make your particle jumps at an extra rate, either right or left. Okay, so right for plus particles and left for minus particles. And this asymmetric part of the dynamics is going to occur at a rate lambda n for the same reason. Okay, you want this contribution to appear macroscopically, so you need to let your particle travel over macroscopic distances. And since the dynamics is asymmetric, the time you need to wait is of order n, so you just accelerate it by a factor n. Okay, well, the subtlety here is that I'm going to enforce, so recall that for MIPS, you need some dependency of the velocity of the particles in the local density. So the way I'm going to enforce that is I'm going to prevent particles from jumping over occupied sites. Okay, so there is an exclusion mechanism, but which is only really enforced over the asymmetric part of the jumps. Okay, because over the symmetric part of the jumps, you allow two particles to swap. Okay, so now you have your asymmetric part, so your particles now are essentially active. And on top of that, you're going to add a mechanism that allows you to flip your particles. Okay, so a plus particle can become a minus and vice versa. Okay, so at rate gamma, you're going to change a plus particle to a minus and vice versa, a minus particle to a plus. Okay, and this part of the dynamics, you don't actually need to rescale it, and it's going to appear at the hydrodynamic limit without rescaling in n. Okay, so now you have three different scalings in n, but as you take n goes to infinity, you're going to get a well-defined macroscopic limit, which I will not define. So how do we define the macroscopic counterpart to our configuration eta? Well, the macroscopic limit is going to be given by a pair of functions rho plus and rho minus, which depend on time and which are functions on the continuous square. Okay, and the way you define this function rho plus and rho minus is you take the discrete integral of your configuration against the test function, and you expect that it's going to converge to the continuous integral integrated against your macroscopic profile rho plus. Okay, you can do exactly the same with the subconfiguration of minus particle, and you're going to recover the macroscopic profile rho minus. Okay, so this defines, provided that this limit actually exists, this defines two profiles, rho plus and rho minus of Tx. And we denote by rho the total density, and by m what I will call the magnetization field, which is the local intensity of the drift. Okay, if there are a lot of plus particles, locally the drift is going to be to the right, and if there are more minus particles, locally the drift is going to be to the left. Okay, so now I have defined my macroscopic fields, and I'm ready. Okay, you can of course do exactly the same macroscopic scaling and macroscopic limits for absolute value of eta x and for eta x, which converge respectively to rho and m. And this is what I'm going to be interested in. So now the idea is that I want to characterize the behavior of rho and m. And of course, rho and m could still be random, but actually you can prove that it's not. And it's called, this procedure, for those who don't know it, is called the hydrodynamic limit. And roughly speaking, it's the law of large numbers for particle systems. And you can prove that you have this convergence. So absolute value of eta and eta converge respectively to rho and m in this sense here. And you can prove as also that rho and m are going to be solutions to coupled reaction diffusion equations. Okay, so if you look at the first equation, you see that the time derivative of rho is equal to the Laplacian of rho. So this is the diffusive part of the microscopic dynamics, plus a drift term, that is the direct consequence of the local driving field, okay, the local activity of the particles. And you see that here you have a factor 1 minus rho in the ballistic term, because you have an exclusion rule over your asymmetric dynamics. And you can perform exactly the same with m. So m is not a conserved quantity, of course. So now you have also a reaction term, which corresponds to the fact that the particles are flipping. Okay. Okay, so you have a pretty you have a well-defined and pretty nice equation for the macroscopic behavior of your system. And actually, this result is not very hard to prove. It's pretty much a straightforward consequence of what's called the entropy method, which is a method derived by Guo, Papanicolaou, and Varadan in '88, in order to find the hydrodynamic limit for gradient systems. Okay, and as I mentioned, so the hydrodynamic limit is just a law of large numbers. So what you're interested in very strongly is the local equilibrium for your system. And here the local equilibrium is going to be just a product measure. And this product measure is parameterized by the local density and the local magnetization field. And you're just going to put a plus particles with probability rho plus m over 2, which is just rho plus. And you're going to put a minus particle with probability rho minus m over 2, which is just rho minus. And you're going to leave the site empty with probability rho, 1 minus rho. Okay, and this and the principle of local equilibrium tells you that locally, if you look at your active exclusion process, well, in a given box, in a given microscopic box, the distribution of your process is going to look a lot like this distribution here, except that and with the parameters rho and m, which are given by the hydrodynamic limit.
So, Clement?
Yeah.
Can I ask you a question? So,
sure.
This model that you're presenting doesn't have product invariant measures.
Doesn't have?
I don't know, have invariant measures, product invariant measures or not?
So no. So you have you can prove local equilibrium in the sense that the local invariant measures are approximated by these product measures here, but the actual stationary state for this process are not product measure. So what you would expect is, okay, maybe you have a chance because for ASEP, for example, the asymmetric simple exclusion process, you have this kind of magic that the product measure are still invariant for the asymmetric version of the model. But as soon as you have two types of particles, it's no longer the case. And this is actually, so I'm going to get back to that in more detail later on, but this is actually why you can have this kind of motility induced phase separation.
Very good. Thank you.
Yeah. So you can approximate the local equilibria for your system, but you don't know exactly the stationary state for your system. Okay, so we have this pair of equations, and the first thing I'm going to do is I'm going to rescale space and time in order to go from 3 parameters, so diffusion, drift, and gamma. I'm going to rescale space and time in order to just have 1 parameter, which is going to essentially be the strength of the asymmetry. Okay, so by properly rescaling space and time, you get to this pair of equations where the only parameter is called the Peclet number. Okay, and it is the parameter in front of the asymmetry here. Okay, so now I have this couple of equations. I have this one parameter, which is the Peclet number, and I want to understand the macroscopic behavior of this system. And once you have the hydrodynamic limits, the first thing you're going to do, and you're able to do pretty easily, is to test the linear stability of the homogeneous profile. Okay, so imagine that you start from an homogeneous profile with constant density and no magnetization. Okay, so which means that initially you're going to put at each site a particle plus with probability ρ0/2, a particle minus with probability ρ0/2, and an empty site with probability 1 minus ρ0. And you define a small perturbation of your initial profile, and you're interested in seeing what the hydrodynamic limit tells you about the stability of this small perturbation. And by looking just at the hydrodynamic limit, you can see that taking this small perturbation is going to vanish as soon as you are in the right range of parameters. And more precisely, you can see that outside of this parabola, which is defined by this equation here, the homogeneous profile is going to be linearly stable. So if you put a small fluctuation on top of your your constant profile, well, this small perturbation is going to smooth out and vanish. Okay, and these curves S plus and S minus depend on the Peclet number, and those are called the spinodal curve. Okay, and of course, inside the spinodal curves, your homogeneous profile is no longer stable. So if you put a small fluctuation in your process, you're going to be able to increase the fluctuation around the homogeneous state and actually create a macroscopic perturbation of your homogeneous state. Yes,
Clement, may I ask you another question?
Sure.
So can you come back to the diffusion equation?
Yeah.
And so in this diffusion equation, in principle, if you have rho and m constant, this is a Shanghai solution only if m is 0, right?
Yes.
And
yes,
then,
because as soon as m is non-zero, even if it's constant, you have a different drift on your different types of particles, so you're going to have some motion somewhere in your system.
Yeah. So what you mean by linear stability is that basically you have your perturbation of your constant profile, and this perturbation goes back to the constant profile.
Yeah, exactly.
The profile goes down.
Yeah.
Okay.
Yeah, exactly. You mean in magnetization it goes down?
Yeah.
Because in density it's constant.
Yeah, exactly.
Yeah, in magnetization it would go down. Okay, so you have linear stability of the homogeneous profile in this region. You have linear instability in this region. And now what you're interested in is what actually happens when you start from this region. Okay, so of course, if you start perfectly from the correct profile, well, it's an unstable equilibrium, but okay, you can remain there, at least according to the hydrodynamic limit. But this is not physically very relevant because if you look at the finite size system, you're always going to have these small fluctuations that are going to drive you out of your unstable equilibrium. Okay, so now we want to understand a little bit better the actual stationary states for this model, and we want to go beyond just the regions of linear stability. So first, in the stationary state, you can expect that you have invariance in x2 because you just have diffusion in x2. And you have also invariance in time because it's a stationary state. So this gives you a pair of equations that looks like that. And if you integrate the first one, well, you're going to get a closed equation for m as a function of rho. Okay, so this is very nice. In this region, we're going to be able to find an equation for the magnetization field only as a function of the density field. Okay, so this specific m I'm going to call m of rho because it's a function of rho. And you see already that the interface length, so imagine that you actually have phase separation. You're going to have a dense region, which is going to be the liquid region. You're going to have a low density region, which is going to be the gaseous region. And between the two, you're going to have an interface length. Okay, and you see from this identity that if the magnetization is finite, and this is the case because m is between 1 and -1, if m remains finite, it means that the interface length is going to be roughly over the 1 over Peclet number. Okay, so what it means is that as Peclet goes to infinity, So the drift you're going to put on your particles is going to be stronger and stronger, and the interface length is going to go to 0. So in the limit where the drift is very strong, you're going to have sharp interfaces between your phases. Okay, so now you can insert the value of m in the second equation, and you are actually able to close the equations for rho, and you are able to derive with a little bit of work the actual values for the coexisting densities, for the liquid and gas densities for your system. And so you have essentially a full phase diagram, which looks like that. So inside the blue region, you have linear instability. The red curves are going to be the phase separated densities. Okay, so imagine that you start in this point here, inside of your blue curves. What's going to happen is you're going to have a small fluctuation, and then you're going to have nucleation of the phase separation, and you're going to create a liquid phase, which is going to be given by this density here, and you're going to create a gas phase whose density is given by this curve here. Okay, so now, okay, this is very nice. We're able to have an actual phase diagram for our system, but it may not be completely clear why, if you start from this region here, you don't have phase separation. Because you see that already you want to go to the liquid phase and the gas phase. You want to phase separate in this region between the two curves. Okay, so that's what I want to talk about now. But to understand that, you actually need a little bit more information than just the hydrodynamic limit, and you need to take a look at the large deviations for your stationary state. So as Milton mentioned in his question earlier, so because we have a weak drift, which is different for the two types of particles, unless the Peclet number is 0, so unless you have a passive gas, the Bernoulli product measures are not going to be stationary for these dynamics. And so what you're interested in is, okay, we have an unknown stationary state. We know that locally it looks like a product measure, but okay, let's imagine that you're able to prove a stationary state large deviation principle. Okay, so imagine that in this unknown stationary state mu bar, you know that the probability of observing roughly the profile rho plus m over 2, rho minus m over 2 is exponential to the minus n squared times a potential. Okay, so this function v is called a quasi-potential, and I don't claim that I'm able to actually compute it, but in order to explain a little bit more clearly what happens in the phase diagram, let me assume that you can actually prove a stationary state large deviations principle. Okay, so the n squared here is just because of the fact that the volume, I'm in 2 dimensions, so the volume is of order n squared. Okay, so if you fix a profile rho, well, you expect, according to what I mentioned earlier, that the functional v of rho dot is convex, and it's going to be minimal at a m, which is this m rho that I described earlier. Okay, so first you kind of removed one of the variables from the equation, and now you're interested in this function v of rho m of rho. This is what I'm going to call, by abuse of notation, v of rho. And once again, I'm going to make an assumption which is completely false, but let me explain why I make it just afterwards. I'm going to make the assumption that this quasi-potential v, which is the large deviation functional for my active lattice gas, is just a function, a local function of the density. Okay, so first I'm neglecting the fact that there are very likely correlations in your system under the stationary state, and I'm also neglecting the fact that f here would most likely depend not only on rho of x, but also on the local derivatives of the density. Okay, so first, okay, this assumption is very likely false, but at least it's reasonable in the limit where the Peclet number goes to infinity, because as I mentioned, then you have sharp interfaces, and you can expect that at least this function f, if it exists, does not really depend on the gradient no more, okay, because you have already created your sharp interfaces. Okay, so now why do I make assumptions that are clearly false? Well, I make these assumptions because it's going to allow me to give a very nice heuristic argument of why you have this interregion here, which is linearly stable, even though you would expect something else. So now the quantity I'm going to be interested in is this function f. Okay, so essentially the density of the quasi-potential. And if I take a look first at what happens is if the Peclet number is less than 4. Okay, so I'm in this region here where there is no phase separation regardless of the density. Well, if this f existed, so imagine that I take the limit where the Peclet number goes to infinity, even though I can't. If this function f existed, it would look something like that. It would be convex. Okay, so if you take a look at the homogeneous profile, where the density is ρ0 and the magnetization is 0, this would be a local minima for your functional V, for the quasi-potential, under the constraint that the total density is conserved. Okay, so what you expect from your initial state is something like that. Okay, you have an homogeneous state that is stable in time. Okay, so now let's go to the more interesting case where the Peclet number is larger than the critical value of 4. Then you expect that I'm going to call it free energy, even though it's not a free energy because you're not in equilibrium, but your functional F probably would look something like that, meaning that you have convex regions and you have a non-convex regions. Okay, so let's take a look first at what happens in a convex region. Well, once again, the homogeneous profile is going to be a local minimum for the quasi-potential because F is convex. And once again, with the constraint that the total density must be equal to ρ0. So if you are in the range of density, which is in these convex regions here, you expect that still you're going to stay in your homogeneous stationary state. Once again, what's interesting is what happens in the non-phase separated phase. So just to get back to my phase diagram, so here you have these two convex regions. And these two convex regions are going to be the two regions that are above and below the blue curve. Okay, so now I'm still at a Peclet number which is larger than 4, but I'm going to look at the concave regions. So I'm going to look at what happens between the two spinodals. I'm going to look at what happens in the linear instability regime. Well, because F is concave, the homogeneous profile is no longer a local minima for the quasi-potential V. Okay, so you still have the constraint that the integral of rho must be ρ0, but since you have the homogeneous profile is not a local minima, with a little bit of a fluctuation, you're going to be able to nucleate your phase separation. So if you start from a density that is in this concavity region here, what you're going to see appear is this phase separated regime. Okay, that schematically is going to look like that. And the question is, how do you compute the liquid and gas densities? Well, to compute the liquid and gas densities, you need to take a look at the convex envelope of your function f. And if you do that, well, you're going to have limiting densities ρg and ρl, which are going to be the places where the convex envelope of f is not equal to f. Okay, you have a boundary where you had to correct f in order to get a convex function. Now, let's take some ρ0, for example, in this region here, and define ρ prime, which is going to be ρg in some domain and ρl in some other domain. Okay, so you have, ρl, in lambda g complement, the complement of lambda g. So you have your phase separated profile, which I'm going to call ρ prime. So now you have to satisfy a constraint because once again, you have conservation of mass. So you cannot create density. So you have a constraint that ρg plus alpha g plus ρl 1 minus alpha g must be ρ0. And under this constraint, you want to compute the quasi-potential of ρ prime, of your phase separated profile. But since my function v is assumed to take this form, well, it's very easy to compute v of ρ prime. It's just going to be f of the liquid phase times the liquid volume plus f of the gas phase times the gas volume, okay, which is this identity here. And since in this region v is not convex, well, you see that v of ρ prime, even under the constraint that you have here, v of ρ prime is going to be less than v of ρ, just by a simple convexity relationship. So this tells you that the quasi-potential associated with the phase-separated profile is less than the quasi-potential associated with the homogeneous profile. And on top of that, you are able to access this phase-separated regime because you are in a concave domain for F, which means that you are able to nucleate phase separation. Okay. Is everything clear? Are there questions?
So I have a quick question about your pictures.
Yeah.
So these are somehow realistic parameters for the hydrodynamic equation. I mean, is you're taking weakly asymmetric particles.
Yes. Yeah. So here at that point, nothing has been sent to infinity. So the only thing that I would not be able to see without taking, for example, the Peclet number going to infinity, I would not be able to see actually sharp interfaces.
Okay.
Okay, but otherwise you can actually see the phase separation for finite Peclet number, which is exactly what this phase diagram tells you.
Okay, thank you.
Okay, so now hopefully this is a little bit more clear why you have these actually three regions. So you have the region between the spinodals where the homogeneous profile is not stable, which is this concavity region for the free energy. You have the intermediate region where the homogeneous profile is actually stable, but it's not the minima for the energy. And you have this convexity region where you actually have the homogeneous profile is stable and it's a minima for the energy. Okay, so now this is all well and good, but of course, so first, the assumptions are made for V are not realistic if the Peclet number is finite, but this was just to give you a sense of probably what happens. And the bigger problem is that in general, you are not able to actually compute this functional V. The only place where you are actually able to compute it is in equilibrium, because in equilibrium, the stationary state is Bernoulli product measure. So this quasi-potential V is just the free energy. And this is the free energy that you would expect. So you know it's very well known that the free energy for just the SEP is rho log rho plus 1 minus rho log 1 minus rho. Well, here instead of two states, you have three states. So you just have to add up the corresponding term in the free energy, but it's very reasonable. Okay, so the physicists would call that the free energy. Probabilists would call that just the large deviation functional for Bernoulli product measures. The second case where you might be able to find an explicit formula for V, or at least get more information, is if you have some nice orthogonality condition satisfied in the context of the macroscopic fluctuations here. Okay, so this is the first problem. The second problem is that my model is a little bit artificial. The reason I say that is if you take a look at the jump rules I introduced, symmetric jumps allow to swap neighboring particles, but asymmetric jumps do not allow particles to swap. Okay, so you have absolute exclusion on the asymmetric part, but you have loose exclusion or swapping exclusion for the symmetric part. So it's a little bit unfortunate because it means, for example, so first it means that physically speaking, your system is not really natural. And the second unfortunate thing is that because of this, because you have different rules symmetrically and asymmetrically, for example, you're not going to have an Einstein relation between the conductivity matrix for your system and the diffusion matrix for your system. Okay, so you have kind of an outlier behavior for your system. So let's try to make it a little bit more realistic. And so one way to do that would be just to remove the exclusion constraint, allow swap also asymmetrically. But then you cannot observe MIPS because MIPS is reliant on the fact that you have a slowdown of particles at high densities. And the slowdown at high densities is exactly guaranteed by the exclusion rule. So the other solution is, okay, let's add up some enforced exclusion on the symmetric jumps. So now, and this is the non-gradient case, I'm going to talk a little bit more about it later on, but it's the non-gradient case where particles are not allowed to jump even symmetrically on a neighboring site if this site is occupied. And it's a non-gradient model because if you take a look at the instantaneous particle currents of plus and minus particles, so this is the current between sites x and x plus 1, you see that those cannot be expressed as local gradients the way they could be in the first model. So this is the first problem, is that this model is non-gradient. The second model is that because you have this full exclusion, your system is not going to be ergodic as the density goes to 1. Okay, so you're going to lose some mixing information or some mixing behavior at high densities. Nevertheless, despite that, you were able to actually prove the hydrodynamic limit for this model, but it's much, much harder than in the gradient case, but still you can do it. And it's actually a particular case of what I did during my PhD. And you obtain this cross diffusion, so diffusion, ballistic and reaction equation, where you have diffusion and conductivity matrices D and S. And you could say, okay, this is all well and good. You have very nice matrices D and S. Okay, those look like they are actually completely determined. The problem is that you see that in both matrices, you see this coefficient here, which is called ds of rho. And d of rho depends on ds of rho as well, through this formula here. The problem is that you don't have an explicit formula for ds of rho. ds of rho is what's called the self-diffusion coefficient. Is the diffusion coefficient of a tracer particle in an homogeneous environment of density rho. Okay, so this ds of rho is not an explicit function, unfortunately. But this time, since we were coherent in the way we chose our jump rates, you recover the Einstein relationship between these matrices D and sigma, and the proportionality coefficient is called the compressibility matrix. Okay, so now we have a little bit more of a little bit more realistic model. It's a little less nice because the coefficients are not explicit, but at least it's more coherent, physically speaking. And now the natural question is, can we do exactly the same as we did for the gradient model? And so the answer to this to the question is almost. So first, let me take a look at what happens at the hydrodynamic level. So you see here that you have this cross term ds of rho, and you have, so in the diffusion matrix, you have these two other terms here. And the cross term actually is going to be is going to represent this phenomena here, where you have essentially an homogeneous total density, but you have some heterogeneities between the two spins. And this ds of rho is going to be responsible for homogenizing this system. Okay, and the formula for ds of rho and the way it applies to this type of model was derived by Castell in 1992. The two other coefficients are much more straightforward. They come from the fact that if you have some heterogeneities in the total density, you're going to have a current in your system. Okay, so I'm not going to spend a lot of time on this. Okay, so the question is, can we do the same? But first, I'm going to try and improve once again my model and try to look at a more realistic model, because I want to remove the assumption that there are only two velocities. Well, there is a very natural way to do that, is to consider a drift, which depends on the particle. So now each particle has an angle theta between 0 and 2 pi, okay? And you're gonna put a drift on your particle, which depends on its angle, and the particle is gonna jump left or right, respectively, with an additional rate plus or minus lambda n cos theta, and up or down with an additional rate lambda n sin theta, and minus lambda n sin theta. So what these jump rates mean is that a particle with angle theta, because of the drift, is going to travel on average in a direction theta. And you still conserve your exclusion rule for all particle jumps. Okay, and now I'm going to change a little bit my reorientation dynamics, because now you cannot have just a flip. Okay, you can have just a flip, but you need to define it. But actually, I'm going to take even a simpler reorientation rule. And I'm going to consider that my angles just perform Brownian motions on the circle. Okay, so this is called active Brownian particles. So particles which are driven in a specific direction, and the direction is going to perform a Brownian motion on the circle with a given diffusive coefficient gamma. And then you can derive, once again, the hydrodynamic limit, which takes a shape which is going to be very close to the non-gradient one with just 2 spins. Okay, except that this one, this time you don't have just a magnetization M. You have a function ftx of theta, which is the local density of particles with angle theta. But you can find a closed equation for this new non-gradient model. The problem is, well, you still have your coefficients, your matrices D and sigma tilde, and these matrices still involve the coefficient ds. And if you want to be able to actually confirm your results with numerical simulations, you're going to need some knowledge of what ds is. So a first option, which would be to just simulate ds and get these values. But actually what we did with a couple of colleagues from Cambridge is exploit a very nice description of ds. And they obtained for ds an approximate value, which is obtained by so-called the match asymptotics method. And they get this estimate ds tilde of rho, which is this function here, which is not exactly ds, because ds a priori has no reason to be a finite degree polynomial, but it's a very good match for ds. So you see in this figure here, so the black line is this function ds of hat, ds hat. The black line is ds hat, and the red dots are simulations of ds of rho. So you see that this new function ds hat is a very sharp approximation of ds, and you can actually prove that it is mathematically sharp as the density goes to 0 or 1. So maybe I should not take too much time to talk about matched asymptotic, but the gist of it is the idea behind matched asymptotics is you're gonna compute the probability under your dynamics to have 2 particles with spin sigma and sigma prime respectively at x, y at time t. Okay, and you want to close down the equation for this quantity here. And the way you're going to close down the equation, or at least close down between quotation marks, is if x and y are very distant, essentially you expect that the behavior of your particles is independent. So p sigma sigma prime is just going to be the product of p sigma xt, p sigma prime yt, where p sigma prime yt is just the probability of seeing sigma prime at y at time t. Okay, so you have some kind of what they call mean field decomposition as the 2 sides are very far apart. And if the sides are not very far apart, you go a little bit further in the equation for p sigma sigma prime. And you try to make the asymptotics match for this detailed version of what happens locally and this long distance mean field approximation. And this you match the asymptotics, hence the name of the method. And what you obtain in the end is this very nice approximation for ds. Okay, so now we have a nice approximation for ds, and we're able to perform exactly the same linear stability analysis for the non-gradient model. So the analysis is a little bit harder. Much harder, because like the equation is less nice. But still, you can perform the same linear stability analysis, and you can obtain, once again, an exact phase diagram for the linear stability of your homogeneous profile. And you see a figure that resembles a lot what happens for the gradient model. And you see that here you still have some discrepancies. And the discrepancies come from the fact that the hydrodynamic, at least I think so, come from the fact that the hydrodynamic equation is much less linear than the gradient one. And these nonlinearities mean that there are other ways to create fluctuations than just a small linear perturbation. Okay, so unfortunately, what's missing here in this picture, we have the linear stability region, but we do not have the coexisting densities rho L and rho G. Okay, and this is much harder because of the fact that the system is non-gradient and that the equations are much trickier to estimate. Okay, for example, it's not possible, or at least we didn't manage to do it, to get an explicit formula in the stationary state for m as a function of rho, which we were able to do in the gradient system. But once again, you see that your simulation actually matched very well with this phase diagram, and you see that exactly in the same way that you had for the non-gradient model, you have emergence of motility induced phase separation for the non-gradient model as well. Okay, so what you see here is the top row is the density, a representation of the density. So the yellow regions are the high density ones, the liquid zones. And what you see below is the magnetization field, the local direction of the flux. Okay, so then this is the purpose of recent work that's ongoing with Maria Bruna, James Mason, and Robert Jack in Cambridge. And just to conclude, so we managed to show that actually even for the non-gradient model, you have motility induced phase separation, or at least we got some information on this emergence of phase separation. And a very interesting thing that actually was put to light by physicists recently is that you don't need a lot of active particles to create MIPS. Actually, if you take just a lot of passive particles and you complete them with a bunch of active particles, you can get MIPS as well. Your system does not need to be completely active. So that's what we're working on right now. Okay, so let me thank you for your attention. And these are a few ongoing works. So the one I mentioned with passive particles, and we have also a project with Thierry Bodineau on the emergence of MIPS, but from a different perspective. Thank you.
Thank you very much, Clement, for your nice talk. So do we have questions?
Maybe can you go back to your last graph and explain a bit more these pictures?
Yeah. So the black curve is the linear stability region for the linearized equation. Okay, so you take you take this equation here and you linearize it, which is relevant if you take a small perturbation. And what you get is this black line here. This is the stability region for the homogeneous profile. And the blue dots are so the blue and red dots are all simulations. The blue dots are simulations where a small perturbation of the homogeneous profile vanishes. So this is the actual, the blue region is the actual stability region for the equation. The red dots are where a small perturbation does not vanish and actually explodes, and you have nucleation for your phase separation. And you see that there is a small region where your interface here does not agree with your linearized equation phase diagram. And the reason is that at high density, the linearized equation is no longer relevant because you have this mixing problem between plus and minus particles. Or at least that's my interpretation of it.
Could you prove anything about fluctuations for these models?
So for the first model, I would imagine that stationary fluctuations are doable. The gradient one, I would imagine that at least the stationary fluctuations are not too hard to get mathematically. For the non-gradient one, I don't have a lot of experience regarding fluctuations for non-gradient models, so I cannot, probably you could answer this question actually. So I don't know how hard it is to derive stationary fluctuations for non-gradient models. Now, out of equilibrium, of course, so out of equilibrium fluctuations is a much trickier topic, but I think it's Milton that proved non-equilibrium fluctuation for the WASEP, no?
Yeah.
And so I have some hope that perhaps is misplaced, that non-equilibrium fluctuations could be obtained for the gradient model as well. Because the phenomenology is not very different from WASEP. The big difference is that you don't have exactly the right stationary states, but maybe at the level of fluctuations, maybe that would not impact the proof, or at least not so much.
Thanks.
So I have a question, Clement, about once again, about your pictures on which you have the green and the red particles.
Yeah.
So in this in this simulation, no, when you have the phase separation, it's a soft phase separation, or it's a hard phase separation, in the sense that.
So you mean hard interface?
Yeah, I mean, you really have this continuity of densities, or it's just that they merge in some region in a kind of smooth way?
No, so here everything is smooth, and so if you are at a finite Peclet number, you cannot have anything that is not smooth, because at the heart of it, it's a diffusion equation with a weak drift, with a drift term. Okay, so of course everything is smooth as long as the Peclet number is finite.
Okay.
If you want to see really sharp interfaces, then you need some proper scaling of the Peclet number.
Okay, and related to that, so do you expect to have local equilibrium in this smooth regime? So I mean,
yeah. So for this model, you have local equilibrium because of the swap. So it's not the case for the non-gradient model, but for the gradient model, you just swap your particles, so you have very good mixing locally. So this is why you are actually able to prove the hydrodynamic limits. And this is why the hydrodynamic limit is just a consequence of the entropy method. Is that because of the swap, you have a nice local equilibrium, you have the proper Dirichlet estimate, you have pretty much anything you want to get the hydrodynamic limit.
Yeah, but I was thinking more about the stationary measure.
Okay. So this is a different question. So I would say that, okay, at the first order, your local distribution is going to look like an equilibrium state.
Mm-hmm.
But you're gonna have some small correction, which is why at the large deviations level you don't have just the free energy, you have the quasi potential, which you don't know.
Yeah.
I mean that's what I would expect.
Okay. Okay. Well,
I have a question.
Yes.
Again, the shock picture, the green and red, please. So here in the right picture, it seems that you don't have a jump from green to red, right? Is that it, the case?
Sorry, you don't have a jump from green to red?
Yeah, because I don't see red, or do you have maybe the picture? Do you have red particles inside the
Yes. Yeah. You can see that there are a little bit of red particles inside the green and a little bit of green inside the red.
Okay.
Yeah.
So these are particles that are trying to go to the other side. Okay.
Essentially,
so you have a flux of particles to the right, green. Okay.
So that's what I'm. So this is what this. Sorry, what is it? Yeah. This is what this equation tells you, actually, is that if you have a local magnetic field, you're going to have a flux.
Okay. Okay, thank you. Very nice talk and nice models. Thank you very much.
Okay, so if there are no more questions, let's thank Clement again, or let's thank Clement.
Thank you.
Nice
And
talk, Clement.
And well, thanks very much for your very nice talk. And we meet again next week, same time, same place.
Ciao.
Bye.
Bye.
Ciao.